Welcome back to the Health Physics Society video series pursuing the truth and promoting transparency regarding the historical foundations of the current radiation protection philosophy based on a linear no-threshold theory for cancer risk assessment. I'm Dr. John Cardarelli, President of the Health Physics Society. In the 8th episode, we learned about Ernst Caspari's research, which did not support the LNT theory, and how Caspari became a fly in the ointment to Muller and the LNT theory. This 9th episode provides a review of additional Manhattan Project studies to address Caspari's findings and Stern's efforts to save the hit theory.
I'd like to go back a little bit and talk again about a couple of the studies. Right now, we've got on the table the study by the PhD student in Edinburgh. We have the Spencer study, which showed linearity, the Caspari study, which showed a threshold, and we also have the mouse study by Charles, which I don't think we've talked about. If we could backtrack to the Spencer study and talk about what was the quality of that study.
Okay, Warren Spencer study was the acute study. So it was looking at all the radiation given at one time, and they gave it from across about 5 or 6 different doses of radioactivity, and it showed a linear dose response. And the Caspari study was the key one because it would be the chronic study that would be compared against that. But in terms of the Spencer study, the Spencer study was generally viewed as a high-quality study. It was, it's been cited widely and authoritatively throughout, ever since 1948 when it was published. But I have gone and looked into this in considerable detail, as I have in all the others. And what I found were a number of troubling things which affect the credibility and really affected, in my opinion, the publishability of this paper.
What was the lowest dose used in that study?
The lowest dose used in that study was 25 rads.
So quite a substantial dose. We're not talking about the low dose range.
Well, they called it low, but that was maybe low for 1943, 44, but according to our standards today, it's very high dose, put it that way.
Yes.
And that was the low dose. Okay, that was the low dose. Now, in this study, they were really trying to determine, again, just like in the Edinburgh study, it was evaluating this total dose versus dose rate hypothesis. Now, in this study, what I found was that it was, of the 5 or 6 doses that they have, they commonly had, for example, the same dose that was tested over 2 different dose rates. So it might have been 50 rads, and then it was tested over dose rates that could have been varied by 250%. And in some cases, they had the same total dose in two treatment groups where the dose rate varied by tenfold, enormously.
That's a lot.
And then what they did, and that would be okay if they presented them separately, but what they did was they combined those treatments into one, so that where you had the same total dose in two different dose rates, they combined them into one group. There's no way that one can possibly do that and expect to try to answer the scientific question that you're trying to answer. And they did that. What made it worse was when Caspari was comparing his data to Spencer, Caspari was looking at the 50 rad dose, and he was spreading 50 rads out over the entire lifespan of the fruit fly. And in the 50 rad dose that was done in the Spencer study, they actually had 2 different dose rates. It was somewhat incomprehensible to me. The other aspect, there are other aspects with this, and that was that they didn't have any effective temperature control. It was done at a time when the fruit flies were actually within the corridor of the scientific building that it was in. This is in Rochester, New York, and it's 1943. And this is done throughout the fall and the winter into the spring and early summer. And it goes through changes of 24 hours. And so the temperature control was extremely poor. Now, when it comes to the Caspari study had learned all the tricks of the trade, that all the things you shouldn't do when it comes to designing a study and conducting it. And so it wasn't that Caspari was a better researcher than Spencer. It's just that he saw what Spencer was doing and they learned from it. And so the things that they had to control, they were able to control adequately in the Caspari study. But in the Spencer study, you had poor temperature control. You had the combining of these various dose and dose rates. You also had very inadequate statistical modeling at the low dose end. It had numerous other methodological issues. Even the calibration of the radiation was of the X-ray machine was done very infrequently, and it was done differentially amongst the different groups. There wasn't anything that was standard that was identifiable there. They had a control group that lasted for nearly a whole year. So they interspersed the control groups, and there was great variability from month to month in terms of background mutation. And so what happens is that they compare one group that was done over 12 weeks with a control group that studied over 70 weeks. And so they're not matched. The treatment is not matched to the control. And I'd have to say, I go back in and I look at these studies, and I see a lot of problems with them. And I'm not a geneticist. I wasn't on the Manhattan team. Wasn't a future Nobel Prize winner. I'm sure they are schooled in whatever methodological aspects that they had to be schooled in. I can go back in so many years after, and I see serious flaws, things that would raise great concerns if I was a peer reviewer or if I was an editor and I saw that sort of thing. I wouldn't want to have that type of a study published in the journal. I'd be very questionable. And yet the interesting thing is that when these papers get published, nobody in the radiation genetics area ever criticizes this work. The only one who comes through later to criticize that work happens to be me. And I find that to be, it's very troubling, because these people were given passes on this, and then the studies were used to, in fact, base policy, change policy, direct the future of the country. And so in the case of Spencer, just as in the case of the PhD work that was done in Edinburgh, I tell you, these studies had serious flaws, and they never should have been used as they were used for changing policies or for advocating new directions in terms of public safety, things of that nature. The Charles study that you also brought up, the Charles was kind of the worst of the whole thing, because that's what we're really counting on. We're counting on the mouse model to enlighten human responsiveness. And in the Charles research, they actually used, if you can believe this, 400,000 mice. It's an awful lot of mice. Even in today's world, it's an awful lot of mice. And they never published a single paper during that time period on it. They published the study started, in the 1943 era, and the whole war goes and completes. 1950, they publish a 3-page, very brief summary of it. And then what happens is that what I gathered from reading the literature, why was it just this 400,000? Charles was a really excellent researcher, very good institution. What happened? My reading, whether this is right or not, but the only answer that I have is that people complained very much about Charles as a perfectionist, as a super perfectionist. He was impossible to please, and he wouldn't let anything go until it was done perfectly correctly, something to that effect. I've had one or two of those sorts of professors in my past, and they're impossible to satisfy. You just can't satisfy them. And Charles seemed to have had that to the nth degree. And then in 1954, Charles had resigned his appointment at Rochester, and he committed suicide in a downtown Manhattan hotel. He did leave a suicide note. 1961, what happened is that people tried to publish a summary of that work that was done really 17 years before, but the field had passed them by. It had no impact on anything.
So all the data from his study was still archived somewhere?
Yes, I've seen it. I got copies, and I have looked at that in considerable depth. But what happened was that major developments happened in mouse genetics in the mid to late 1950s, and it changed the direction of the field considerably to new questions. I'll go into this later, but what I'll just allude to this, and that is that in 1958, a major discovery occurred, and it was to show that there is such a thing as genetic repair to radiation damage, DNA damage in the mouse. And once that happened, there's a whole set of new questions. And the questions that they were interested in 1943 with mice were not the questions that were the most important questions. And the Charles legacy, you might say, became a footnote, and a disappointing footnote, an embarrassing footnote to like the Manhattan Project. And so they got nothing of consequence to society out of 400,000 mice and a big focus on the mouse. And because they got nothing on that, I mean nothing, what happened is that everything had to double down on what? It had to double down on Drosophila. Drosophila not only had to give some insights into mechanisms, but now Drosophila is going to be used for what? For human risk assessment. I don't think that anybody in their right mind would ever want to use a fly, fruit fly, house fly, blowfly, green fly, any fly, to establish human risk assessment. But the U.S. government was going to have to do that, and it's exactly what happened.
So Charles' research was going to kind of replicate the fly research in the sense that he was going to do a large dose or a series of total doses to a group of mice and have the control mice, and then also do the drawn out continuous low dose rate, totaling the total dose.
No, Charles was more limited. He was simply going to do a very broad dose-response relationship, and he was not going to be testing the other hypothesis of total dose versus dose rate.
Okay, thank you.
Yeah.
Thank you for clarifying that.
Yeah.
So where does that leave us now?
Well, I can tell you where it leaves us. It leaves us with that suggestion from Muller, because Muller sees that Caspari has thrown everything up into confusion. Because Caspari says, I think that it's a threshold. And all his colleagues, and I mean the colleagues, the field of radiation and genetics, they're not believing in a threshold at all. He has challenged the hit theory. And so what happened was, and I have various sorts of letters from people that they shared, the Caspari study with, and they said, how can we save the hit theory? Well, the way that they were going to try to initially save the hit theory, other than confuse people with these publications and tell them not to take the data seriously and all these other really what I'd consider inappropriate responses, they actually tried to do something that was responsible. They got some money from the Atomic Energy Commission, and they were going to try to replicate the Caspari type study. Just so happens, unfortunately, that as World War II ended, so too did the talent that was around Rochester decided to go elsewhere. So Warren Spencer, who's a very talented man, he went back to the College of Worcester, where he had a job. And then there was Ernst Caspari got a job at Wesleyan University in Connecticut. And so these people life was beginning anew after World War II. And so Kurt Stern did get the money, and he wanted to test this Caspari finding. So what he did was he had to turn to a very inexperienced, brand new master's student that was arriving at Rochester. And this person's name was Delta Uphoff. And so delta becomes a central player in this story. And this is this is really the Manhattan Project, and she's trying to see whether the answer's correct or not. And so what happens is that she gets involved with doing 3 big studies. So
these are all flies again, right?
Fruit fly, yes,
Fruit flies.
yes, and so what happens is now I have the data for all 3 studies, and I have a lot of correspondence that relate to this, and so and Muller stays involved in his role as a consultant, and so what happens in the first study is that a problem happens. And the problem, because they've been sensitized to this issue of the control group, and they had a fight over the control group. What was the legitimate control group's background mutation rate? They had to go into the literature and so forth. And so, as it turns out, when Delta came in with her study, when it took almost 8 or 9 months to do this, what she finds is that her control group is reading about 40% below what is in the field, and 40% below what Caspari's is.
So they have much fewer mutations.
That's correct, in the control group. And so what happens is that Stern and Delta, they have to write a report to the Atomic Energy Commission that's funding them. So they write the report in the form of a journal publication. That's kind of how they did it. And so within this write-up, I was shocked, because I got this document. It had been classified by the AEC. Nobody could get it, but it got declassified. I got a copy of it. And when I read this report, what I learned was that they identified this very low control group. And they claim that because the control group was so low that the data were uninterpretable. They write that in the discussion. The data, we just couldn't interpret it because the control just seems extremely aberrant. And something happened, we don't know what happened.
I'd like to ask a quick question. So the control group and the group that's going to be irradiated, are these all the same?
Yes, they are.
Okay. So they just pick out some number of flies and assign them to the control group, but they're really all drawn from the same group.
That's correct.
So they should all have the same background.
Yes, in fact, they were drawn from a special strain that Muller gave them, called the Muller 5 strain. So as it turns out, in the write-up of the discussion of that study, a really weird thing happened, and that is that Stern and Uphoff, their co-authors on this, they blamed the control group findings, the low control group findings, on investigator bias. They actually claimed that. And so who was being thrown under the bus in this write-up? I've never seen that happen in any paper before in my life.
How would an investigator be biased to select a control group with a low mutation rate? In what way would bias play a role in that? Well,
it wasn't explained in the write-up. It was brought in. It was not explained. There could be different ways that you could look at how the study was conducted, designed, and what you called a mutation, what you didn't call a mutation.
I see.
There could be close calls that maybe you weren't. Maybe there was blindedness. There wasn't double blindedness. There are different ways to look at how this was carried out. But whatever it was, I found this very interesting because this suggested to me that there was for them, but I'll assume that this was really written by Stern, because she's a master's student and he's a very established person, that he probably was throwing Delta under the bus, probably not himself. I mean, informing the funding agency that your data is not interpretable and that there might be, more likely than not, there was investigative bias. And where did that bias start? And was that bias present amongst the whole team? Was there bias before Delta even arrived? How long did this occur? This to me was such a troubling thing. And then later when they would ultimately, so what happened was that this was a very serious issue. And so they discounted a whole year of research. Our data are uninterpretable, blame it on investigator bias. So then Delta goes in and does a second study to try to maybe get this one to come out right. Unfortunately, they have the same problem with the control group. It's reading about exactly the same. And so they have the same sort of problems with it. And so study number 2 doesn't work out well at all. This is serious stuff. This is after the war now. He's trying to get this thing right. And they have given him extra money to get it right. And so then they do a third study. For that third study, he accepts a job to go out to UCal Berkeley. And she follows him out there to be the technician, graduate student, and so forth, to do all this work. And the third study, the control group came out okay. That one looked all right to me, and I think everybody else. However, what didn't come out all right was they're assuming there's a linear dose-response relationship. And the response was about 3 times higher than what the LNT would predict. It was way off. And so when I looked at it, I said, everything went wrong on this study. You had the first 2 were low controls, the second one is aberrantly high. And when you really look at what happened at Charles, you couldn't use anything, and you looked at what happened in Rochester and now at Berkeley, it's like the whole genetic aspect of it was just not good. And so what does Stern do? Well, Stern knows that Charles isn't doing anything. And so he decides he's going to do something. So, and this is a big deal what happens next. Stern, now you have to understand that Stern has he's got the Spencer study, which they're saying was linear and was great, even though I pointed out that there were serious problems with that study. They have the Caspari study, which they hate, and they wanted to deep six, you might say, by blaming it on a high control group, right? And then they have the 3 delta studies, the first 2 that you can't interpret, and they might be biased, and the third one is showing an exaggerated response that far exceeds anything that an LNT would ever show. It doesn't look good. But Stern is able to pull a rabbit out of a hat. And what he does is now all this stuff that I'm sharing with you has been written and was shared with the Atomic Energy Commission, but I get all these and I read them all. And I get backup information on them via Stern's papers and other things that are saved on them. And so Stern decides that he's going to write an article for the journal Science, top journal again. This time he writes a single page, a 1-page technical note, 1 page in which he does a type of meta-analysis of these 5 experiments. But what happens is that he now, the Delta papers, the Delta research that was uninterpretable now becomes interpretable. It's now fine. There was never any problem with it.
By combining it with the other data? Or?
Well, he just gave it a blessing, and nobody actually knew, except me and maybe Delta and a few others that were close, that the data were uninterpretable. Now, maybe somebody in the Atomic Energy Commission knew if they read the write-ups. But when he submits it to Science, he doesn't share with the science editor and the reviewers and the scientific community that about 6 to 9 months before, the Delta Uphoff paper data that we are now sharing in this little technical note was uninterpretable and likely the result of investigator bias. So they make that totally silent. And so nobody knows that. And so then they also go back and they refloat the problem of the Caspari control group. It was too high, and they want to discount that. So when you take the Stern paper and you take the 3 somewhat defunct papers of the Delta Uphoff group, you then can create a beautiful straight line linear dose-response relationship. And that's what they publish in the Science paper. And then at the same time, I mentioned it's a 1-page paper. And so there's not the methods and materials and all the supplementary data, all the kinds of stuff that goes into making a real scientific paper. So the last sentence or two in that write-up, they say, And we will be providing a very detailed paper with all our methods and materials and all the backup data. And this will be coming up in a forthcoming paper, and you'll see the real basis of everything. Well, I can tell you that they never published that follow-up paper.
Really?
Yes, really. And so what happened is we are left with this paper in Science. It summarizes the whole 6 years, whatever it was, of the genetic research that the Manhattan Project was all about. It's one page. It's one page in Science, and it's got a flawed. It has a flawed Spencer study, the uninterpretable delta studies, and then basically an abused and discarded comments on Caspari. That paper, which advocated LNT, became the most cited and most important paper that led to the U.S. government accepting LNT.
Thank you for watching the 9th episode on the historical foundations of the linear no-threshold theory, where we learned about the lack of results from the mouse studies led by Donald Charles. We also were introduced to Delta Uphoff, Stern's graduate student at the end of the war, and her 3 study attempts to replicate Caspari's threshold findings. We also learned how Kurt Stern pooled strength and weaknesses from each of these 5 studies to produce a short publication in Science to summarize the Manhattan Project's radiation research on genetics in an effort to save the hit theory. Finally, we learned that Stern and Uphoff never published their detailed findings in a peer-reviewed journal after promising to do so. The next episode, we will explore the post-war efforts to incorporate the linear no-threshold theory into U.S. regulations and policies. Were those efforts transparent and objective? Continue watching to find out and make that decision for yourself. The HPS is a trusted source of radiation information. We're a scientific organization, and as is offered with the scientific peer review process, viewers are encouraged to send comments or suggested corrections to factcheck@hps.org, and be sure to include your sources so that we may correct the record if necessary. If any changes are made, they will appear at the end of this episode. Please visit Ask the Experts website to ask questions or seek answers to common radiation-related questions, and view our fact sheets. We also have official position statements that can be found at hps.org. Finally, if you wish to join the Home for Radiation Professionals, please visit the link below. We welcome you.